In this video, which is a visualization of a bound quantum system interacting with electromagnetic radiation, we analyze it transitioning from a stationary ground state to an excited state under a harmonic perturbation. We first observe the ground state of the bound system, designated as the 1s orbital. This wave function determines the spatial probability density, being the square of the absolute value of psi. We now introduce an external electromagnetic field. This field perturbs the system, altering the kinetic energy operator in the Hamiltonian. We see the incoming radiation ray as a traveling Gaussian wave as it collides with the bound atom. The electron cloud absorbs energy, initiating physical oscillations modeled by the time-dependent interaction Hamiltonian, H'. Since the interaction drives a quantum transition, the spherically symmetric ground state wave function morphs into the first excited state, the vertical 2p orbital. We mark the equatorial nodal plane at y = 0, which separates the top green and bottom magenta lobes, representing the opposing phases of the new wave pattern. To calculate the rate of this transition, we use something known as Fermi's golden rule. The transition probability per unit time, W, depends on the square of the transition matrix element, which integrates the initial and final wave functions with the dipole operator. For this integral to be non-zero, the initial and final states must satisfy strict angular momentum conservation. This confirms that radiative atomic transitions are not arbitrary jumps, but are rather the precise mathematical restructuring of bound wave patterns, governed by the electromagnetic potential and quantum parameter constraints, which has many applications on things like metamaterials, a topic for another video.